Well, it's 8:40 and nobody has come to office hour yet. Bad, bad, bad. Anyway, I got a request from Damien to take a look at a couple problems to try and explain when do you use what when. So I picked a couple problems from the book to illustrate what he was asking about. So let's go ahead and do a little bit of sharing here. So I'm going to share, let's go ahead and share my whole desktop with you. Okay, so this desktop that I'm sharing is got, yeah, you go away, thank you, I want you to go away now, is got problem from 3.8. It's the capital assessment pricing model. It's a financial model that assumes returns on a portfolio are normally distributed. Suppose a portfolio has an average return rate of 14.7% and a standard deviation of 33%. A return of 0% means the value of the portfolio doesn't change. A negative return means the portfolio loses money, and a positive return means that the portfolio gains money. Okay, so the asks us a couple questions. The first one is, what percent of the years does the portfolio lose money? That is returns less than 0%. And the second one, what is the cutoff for the highest 15% of annual returns for this portfolio? Okay, so a couple of hints on how to go about working this problem to get some ideas to help you figure it out here. So let me give myself a little color bar thingy here, but out of my way, there we go. Okay, so if when you're reading, if you notice the first thing here, that it says it is a normal distribution, a normally distributed set of data. So what that tells me is that I know that the model that I'm going to be working with in terms of the shape of the distribution is going to be the bell-shaped normal curve, where this x-axis right here is going to be equal to the percentage return. All right, what else do I know about it? Well, I know, excuse me, I know that the mean here, that mu is equal to 14.7%. And I know that sigma is given to be 33%. So that means our model that we're going to use to model this with is normal 14.7 by 33, where that's the mean and the standard deviation respectively. Okay, so let's go see if we can answer this first question. It's always a good idea to start off with that. You know, what model am I using? What probability model am I using to make my calculations? And then once I've done that, I think the frog got on my throat. Sorry about that. Once I've done that, then I can go about trying to work on the calculations. So first off here, they tell us that we want to find a return less than 0%. So come into our distribution here, 0%, I don't know, say roughly about there is where 0 resides. And they said less than 0%. So this shaded region right here, that represents the probability that x is less than 0. Okay, so that shaded region will be that probability if we can calculate that. So once I know that I'm looking for that shaded region, in other words, that's what I want to know right there, I know what tool from R to go pick up on, okay? I know that what? This is going to be using a p-norm. So this is going to be the same thing as saying p-norm. Okay, now what do I got to put into p-norm? Well, I got to put in the left tail cutoff point, because this is going to be a left tail. And so that left tail cutoff point in this case we know is 0. Then I got to give the mean to the distribution, which is 14.7, and I got to give the standard deviation, which is 33. All right, so let's go bop over to R here real quick. Let's see, where's my R hiding? Oh, where? There you are. And let's go ahead and put that into the console here. So we're going to go p norm, and then 0, comma, 14.7, comma, 33. And so what that tells us is that about 32.7% of the time we're going to get that. Okay, let me just go check that real quick, make sure I'm not going insane here. Give me just a second to go find it here. Okay, I was having a moment of doubt, but I went and checked in the solutions manual, and by Jove, I've got it right. Okay, so that is correct. I don't know why I was doubting myself, but sometimes you know how that is. Doubt just creeps into your head, and then next thing you know, you're not sure whether you're going up or down. Okay, so if we go back one more time, go grab that number out of our studio, looks like we've got, what, 33% of the time, roughly, we're going to lose money. So get back over here, so it's about 33%. Or if you want to write it out, so maybe it doesn't look quite like the standard deviation, you can write it as 32.8%. How about that? We'll go two places. So 32.8% of the time. Okay, so notice that is the percent of years that the portfolio loses money. That's a lot of years. And that's attributed to the very high standard deviation. When you have that big of a standard deviation, it's just a lot bigger than the mean, you're going to get some wacky behavior. Okay, so that takes care of problem one. Let's go take a look at problem, not one, but A. Let's go take a look at problem B. So let's get ourselves a fresh drawing here. Same distribution, same model, but just get a clean copy of it here. So that mean is still at 14.7. And the standard deviation is still at 33, okay? Well, this time, they want to know what is the cutoff point for the highest 15% of the returns in this portfolio. So what they're giving us this time is they're telling us this area right here. They're giving the area, okay? Now notice in the last problem, they gave us the position on the axes, but this time they're telling us that that's 15% right there, okay? And what they want to get from us, what they're asking for, is they want to know what is the value of X that yields that 15%. In other words, if we were doing this as the probability of X being what? Well, greater than, let's call this, just to make it so we have a letter here, let's call this little a, okay? So the probability of X being greater than little a is going to be equal to 0.15. And the $64,000 question is what is that number right there? That's the cutoff number, okay? So to get that, we're going to use QNorm and R. QNorm is the command we want, but we have to be a little bit careful because QNorm, as with almost all probability tables that you're going to come across, works from the left-hand side, just like PNorm does. In other words, what QNorm is going to want you to give it is this checked area over here in red. In other words, it wants to get the 85%. So if you give it the 85%, it's going to be a happy camper and it's going to be able to do this for us. So what we need to do is come in using the command here to figure out what A is. I think I'll come up here and do it. We're going to go QNorm. And we have to tell it the area from the left. That's going to be 0.85. And we got to tell it the mean, which is, in this case, 14.7. And the standard deviation, which is 33. All right, let's go find our studio. There we go, and let's go ahead and do that. So that's QNorm, 0.85, comma, 14.7, comma, 33, okay? And it tells us that 15%, to be in the top 15% of returnees, you're going to be getting back roughly 49% or 48.9%. So that's a pretty healthy return on your investment, okay? So hopefully this is making some sense. At least that's my goal here. So we got 40, what was that again? One more time, make sure I get the right number there. 48.902%. Okay, cool. All right, let's go take a look at another problem, all right? I got one more style of problem here to help us kind of get the hang of these probability distributions. Now, the normal probability distribution is always pretty much going to be stated in the problem. If we go back real quick to the last problem we just did, notice they told us up front, use the normal distribution. They're going to give you that, and that's going to be fairly common. So you have these tools, P norm and Q norm, that you would use for calculating either position or area within a normal distribution. But they're not the normal is not the only style of distribution. There's also the binomial, which is a really good probability model for cases where you have two possible outcomes, where you have that duplicity that happens in a Bernoulli trial. And so those outcomes are usually referred to as success and failure. So in the case of playing a game with the dreidel, it has four sides to it. It's a spinning top with four sides. And they want us to come up with some probabilities based on the success of seeing certain events. But one thing to notice is that in all cases here, that our binomial model is going to be, the probability of success here is going to be equal to 0.25 because there are four sides. So the probability of seeing a none, a hey, or a gimel is all going to be 0.25. And they told us, back up here in the problem, that exactly that. They said each side was equally likely to come about. So that means that 0.25, or a quarter of the time, is what's going to be equal to our probability of success, or our P, okay? And then they also gave us the number of trials. They told us that n here was equal to 3. Now, there are some other things we need to consider for using the binomial model. We need to consider whether or not we have independence of events, which means that knowing the outcome of the last event tells us nothing about the future events, and that probability remains constant throughout each of the trials. And in both of these cases, it does, because it's a randomizing little, top there, right? So our model, our binomial n by p, is going to be 3 by 0.25. Okay, so now that's a good first start. That knowing what the model we're going to use, just like in the last problem, really helps us know what to do next. So in part A, they want to know at least one none. Well, the probability model in the case of the binomial is discrete. It means that you can only have countable number of outcomes. So if the outcome here that we're looking for is a none, you could have rolled the thing and got none nuns. You could have got one none, you could have got two nuns, or you could have got three nuns. So the probability of at least one none says what you're looking for is the probability of, let's assume this is our x-axis here, probability of at least one none is the probability of x being greater than or equal to 1. So let's change colors here for a moment, so maybe make more sense. Okay, so probability of x being greater than or equal to 1 is at least one none. At least one none means I could have got one none, I could have got two nuns, or I could have got three nuns, right? Well, notice that what's left over, all that we've got left after that, is the probability of no nuns. So I know that the probability of at least one none plus the probability of x being equal to 0 has got to be equal to 1, because those total probabilities have to sum up to 1. There's no other way about it, okay? So I can get the probability of the green stuff, the stuff I'm looking for, by taking the red stuff away from 1. In other words, the probability of x being greater than or equal to 1 is equal to 1 minus the probability of x being equal to 0. Okay, now you have to be careful, just as we were working with the normal distribution, about which tool am I using. In the normal distribution, the two tools in R that we're going to be using are P norm and Q norm. In the binomial distribution, the two tools that you're going to be using are going to be equal to our D binom, the D binom, and the Q. Excuse me, not the Q, and the P binom. Those are the two that we're going to be using here. All right, and as in the videos that I've done earlier, that the D binom is, just that one, another one. I just want that one. I want a single value. So when I'm going with a single value, right, then I know I'm going to be using the D binom. So this is for a single value. This is for an x equals, all right? So if I have the x equals situation, I use a D binom. On the other hand, if I have a situation where I have an x less than or equal to, an x greater than or equal to, etc., then I'm going to want to consider using p-binom because that's cumulative. But the default for the p-binom is just as it was for p-norm. It's going to sum from the left-hand side. You got to get a little tricky when you use the greater than. Okay, so let's go back over here and let's actually write down in R what this would look like. How would I calculate this in R? Well, it's going to be 1 minus, oh, well, look, it's an x equals, so I'm going to use d-binom. And then I got to put in there what? Well, I got to put in x, which is 0. I got to put n, which is 3, and I got to put in the probability of success, which is 0.25. So the structure on both of these is the same. You got to give it x, you got to give it n, and you got to give it p. And you got to give them in the right order. You can't mix up the order or it's going to get confused. Okay, that's very important. All right, so let's go over to R and let's go do that. So that's going to be 1 minus d-binom. And then that's going to be 0, 3, 0.25, okay? And I get the following. So it tells me that about 59% of the time, if you want to think about it that way by rounding off, that I'm going to end up getting at least 1 none out of 3 rolls. And intuitively, that kind of makes sense if you think about it. I mean, you would expect that you would see a fair amount of them, okay? So let's go ahead and we'll put our answer back out to 3 places over here. Got here, and we're going to write that down as 57.8% of the time, okay? All right, so that's part A. Let's go take a look at part B here. So our part B, we want exactly 2 nones. So if we go back and look at this again using, instead of drawing a bell-shaped curve, I make a number line because in the case of the binomial distribution, what you're doing is counting the number of successes. So when they say exactly 2 nones, then they just want this one right here, and that's it. So that's the probability of x being equal to 2. And notice again, I'm using an equals here, so I'm going to be using the d-binom. So that's equal to d-binom. And I'm going to put in my 2. I'm going to put in my n, which is my 3, and I'm going to put in my probability of success, which is 0.25. So if I go back over and actually put that into R here, it's going to be d-binom. And I'm going to put in the 2, the 3, and the 0.25, and I hit an enter, and it tells me about 14% of the time I'm going to hit exactly 1 none, okay? So it's like what, 14 point something or other there. So it's 14 point, let's go see what's the dig again. 14.1 if we round off, 14.1% of the time, okay? All right, let's go take a look at C. So in part C here, it says exactly 1 hey. Well, notice that the probability of success for a none is the same as it is for a hey, as it is the same as it is for a gimbal. Remember what I said, this model is going to be the same for all of them. So 1 hey, now we're counting hey here instead of nones. 0, 1, 2, and 3 are my possible outcomes again. And the only thing I'm looking for is exactly 1 hey, so that's right there, all right? So that's the probability of x being equal to 1, which is equal to d-binom of 1, 3, 0.25. And I'm going to let you run the R on that yourself, all right? Okay, so I'm going to clean my screen up here just a little bit so I can get some room. Actually, I'll tell you what, I'll just go get a fresh window. Let's do that because I am out of space on this one. Let's go grab a fresh blank place to write here. Okay, so the last problem, they say at most 2 gimbals. Okay, so get back to the right screen here. So let's go again, doing the same thing. We're going to get no gimbals, 1 gimbal, 2 gimbals, or 3 Gimels. And again, this is my x-axis again, which is the binomial probability, excuse me, the binomial random variable, which is counting the number of successes. So let's take a look here. So what do we want? We want at most 2 Gimels. So at most 2 Gimels means what? Well, it means 0, 1, or 2, right? Because you can get any of those and that counts. So that says it's 0, 1, or 2. So if we write that down, that's the probability of x being less than or equal to 2. Now, if you go back and look at our discussion that we just had a minute ago, when you have a less than or an equal to or a greater than or equal to, then you're going to be using p-binom, right? Now, with the greater than equal to, what we saw over here earlier was that what? You have to be tricky and use the 1 minus trick, right? But if it's a less than or equal to, you're in luck because it's built in. That's the way it does it. It sums it from the left. So, cool beans, this is p-binom. I got to give it the cutoff point, which is 2 by 3 by 0.25. Okay, so how would that look in R? So let's go grab that in R. So that's going to be p-binom. And notice it's giving me the autocomplete, which is so nice. Just hit a tab and that gets it there for me. And I'm going to put in a 2, 3, 0.25, hit an enter. And I get back that about 98.4% of the time, I would expect to see at least 2. Let's go back over, write that down. So that would say about 98 point, I can never keep the stinking numbers in my head long enough. 4, yes, 98.4% of the time we would see at least 2 Gimels, okay? All right, well, I'm hoping that that helps for you, that's a little bump start perhaps on these problems. And it's now 8:58, which means I'm signing off and this office hour is over.